Very happy to introduce our first technical talk of the day after Paul's really lovely keynote, which, like I said, I think introduced so many themes throughout so much on the floor. We'll be spending the rest of the day unpacking a lot of those. Ayse is a member of our advisory board on the magazine and also a full professor at Ryerson University. And one of the things we find on the magazine is that a lot of the best connections we have are with people that kind of go back and forth between the university world and industry. So Ayse is currently the founding director of the Data Science Laboratory at Ryerson, doing a lot of interesting work on data mining. Prior to going into research, she's had a long list of industry positions as well. So she was the deputy CEO of Citibank in Turkey, the COO, CIO, and financial controller of JP Morgan in Turkey, a regional director of advanced technologies at Citibank in the UK. Okay. She also is very kind. Even though I don't speak Turkish, she lets me hang out with her sometimes. So, Ayse?
Thank you. Good morning. Can you hear me? Yeah, okay. So, after Paul's speech, I was a little bit nervous because, first, very politely said technical talk, but, I'm kind of scared to be boring after that lively introduction to big data. Today I would like to talk about, give you a different perspective on big data and big data applications by taking you to my small world, if I may say that, when I think about this talk and today, I was just thinking that although I've been doing a lot of data mining and dealing with big data applications, this and that, but in reality, all I do is I work in small data. So whether, sampling from big data or understanding patterns and, what's going on in the big data, either before and after, always my work is in small data. And I just would like to give you, my view on why small data may be important when we are dealing with big data applications. And also I would like to talk in the context of software engineering because in industry I was sitting on a different chair managing software projects and technologies for major banks in the world. And then when I switched to academia, I took that experience and worked with industry partners to try to solve their day-to-day problems in managing their software development processes. So, and all I did was software analytics over the past 13 years as a researcher. So it's going to be in the context of software engineering, not, in general big data. So why do we need analytics in software engineering? Is it really important that we have analytics? We make decisions like in every field in software engineering under a lot of uncertainty. So we try to answer certain questions, how to allocate our scarce resources, when to stop testing, when is the product going to be ready for the next release, and how confident we are with our processes, our people, product, etc. And then, most of the time, all of these decisions are, although, we use data and data-driven decision-making techniques maybe, but in most cases, no matter how big or mature the organization is, we have experts who make these decisions on a day-to-day basis. However, these experts, like all of us, we carry certain biases. We have our own experiences of previous situations, and we think that this is the way we've always done in the past, and we bring our bias, rightly or wrongly. And sometimes we see that those experts may not be available in the organization. They may be busy with other things or, traveling or whatever. And sometimes we see that in certain organizations, there isn't enough experience to be able to call an expert. So I remember 20 plus years ago when I took my first managerial job in the IT department of JP Morgan, I couldn't sleep at night because I was making all kinds of decisions. I wasn't really 100% sure. I was too young and too inexperienced to take such a job. And it happens to all of us. So in these cases, we really need certain tools to make things easier for us. So I think data analytics is really necessary in software engineering and managing our job in software engineering on a day-to-day basis. However, when we look at the tools, data, and everything we do, we see that the landscape is still quite scattered. And we all use different code versioning systems. And I've seen in the same organization, people may use different code versioning systems from one team to the other. And we have different code metrics repositories, issue tracking systems, and then within the company or together with academic partners, when we do research, our results seem to be non-generalizable. And then it raises a question that what's the point of doing all of this work of collecting data, making analysis, and if I'm not going to be able to take it from one project to the other. I just want to take a step back and make an argument here. I've been working with cognitive psychologists for the last 5-6 years to understand human behavior and how it impacts their decision making in their work in the context of specifically software engineering. I don't know if you have heard Kahneman. How many of you are familiar with Kahneman? Yeah, quite a few. Great. So he is a very famous psychologist, and I think he got the 2001 or 2002 Nobel Prize on his theory. He applied his theory in economics, prospect theory, which basically is the analysis of cognitive biases in human beings and how it affects their decision making, and particularly in this case, the economic systems. And what he says is that we have our brain has two sides. One side is fast thinking, the other side is slow thinking. So when we make decisions by default based on heuristics and based on our prior knowledge. However, most of the time, these decisions are very much error prone. And they did a lot of empirical work with famous statisticians, and they asked questions, basic statistics questions to these guys. And in all of the cases, those famous statisticians failed to give the right answer because of the fast thinking mode of their brain. And the slow thinking mode is actually reactive, and it's triggered by the fast thinking, which is basically using mathematical reasoning skills and logic when solving a problem. However, again, slow thinking mode is clouded with the fast thinking mode. So why am I talking about this? So if we take the software engineering setup and the expert having the fast thinking mode, working in deadlines and has to make decisions in a very fast manner. So can we plug in a recommender system which becomes his slow thinking mode, but works very fast and efficiently to give the right answers whenever the fast thinking mode is making errors. So in this sense, when we think about big data techniques, they fit very well in software engineering, and they can act like our slow thinking mind and saves us making mistakes in decision making. But still, it's not easy to build those recommendation systems, and it's not it's not easy to put together all the necessary information, because when you look at years of our community's work in research and in industry, we still see that it seems we can't agree on certain principles and ground rules. So we make an analysis and say that X metrics works well, but Y metrics doesn't work well here, or vice versa in another situation. So we have scattered research clusters. And it seems that we have a very limited understanding of the people in the field. So we capture information on the product, process, and all that, but we cannot understand the people who actually write the code, make the analysis, and do the testing. So these are, to me, overlooked research clusters. And as I said earlier, we don't seem to have generalized results from one project to the other, from one company to the other. And then there is always a criticism that in software engineering, empirical software engineering research, there is lack of theory, that we cannot base our analysis on a given theory or generate theories. And also, data collection and sharing is always a problem, because every company's data is private, and there are concerns of sharing that data. And if we don't have available data, just like in genomics or something like that, we don't have enough researchers to try on the shared data and come up with better models and maybe theories and generalizations. So these are the general problems when we talk about analytics and advancement of analytics in this field. So maybe the vision is that we use analytics techniques to work like our slow-thinking human brain, and then create models with humans in the loop, and create tools to support people on the field. And again, in the next two issues of IEEE magazine, the software analytics two issues, we also had an article, and we looked at our past performance of deploying these models in the industry. So we've deployed more than dozen models in various organizations. And we have seen that some of the models were very successful and used by these organizations. And we wrote papers together and shared the glory and success of these techniques and models in real life. And but going back now, after maybe a couple of years, these models were stopped, and they are not using it anymore. So yes, at the time of the deployment and shortly after that, they were used, but they weren't sustainable. So we looked at why this was the case and what is the lessons learned for researchers like us and for other companies to share. And we found out that these models were not sustainable because they were not embedded in the processes of these people. And so that's why the tool support at every stage is very, very important. Not only the collection of data and making certain analysis for managers, but it has to be a seamless part of the developer or the tester and embedded in their daily life, and should create value for them in order for them to be sustainable. Otherwise, all of these analytics efforts becomes, nice to have projects, and, we can generate a couple of papers and that's it. So, as I said, we really need to understand how we can embed into the processes, and we should avoid number crunching exercises. Of course, I'm talking to myself and the academia in this case, that we really need to understand what goes on in the field, and we should not get carried away with the beauty of our algorithms and models if they have no use and they can only be number crunching exercises. So this is, where we are. We are all scattered, and we would like to be, helping people creating these models and be sustainable, not only to predict the future, we would like to cause the future together. And so with this introduction to why we need and why we believe that software analytics is important in software development organizations, now the question is that how are we going to do it? So in terms of data, is it really important to have big data? So do you think the size is important? Or how it works? As I said earlier, when I thought about it, yes, we have data coming from all sources in a given company, especially big companies like IBM's, Microsoft's, and SAP's. But then at the end of the day, we really do work on small data. So I say that details are important, and some important patterns are hidden in the big data that could only be understood by looking and focusing on smaller chunks. And also there are all sorts of issues of accessing the data, storing the data, and processing the data in a day-to-day life. So I think it's more important to have meaningful data rather than having any data. So earlier Paul mentioned about some sales data and churn data of telecommunications companies, so how we can sell, cross-sell, and all that stuff. Maybe in marketing it's important to have any data, but I don't think in our field it's that important that any data may not make sense. And so I also believe that there is a point where returns, diminishing returns, that after a certain point, maybe having too much data is not that useful. So another thing I would like to mention is that people use big data as equivalent to data analytics. It's not necessarily. So we do analytics with any kind of data. It doesn't have to be big. And especially in software engineering, I found more valuable and useful to have context-based case studies to support big data applications. And also, going back to my Kahneman example and the analogy, we are the creators of these models. And so we also carry our biases in creating these models. We use certain model assumptions, and we determine certain parameters. And how are we going to make sure that those biases will not create wrong results? And I think on Monday, during the summit here, there was a session on machine learning and human interaction. And there was an excellent example of having human being doing certain tasks, and when they make a mistake, you don't give them more data to train how to do it right. Rather, you take that person and explain where they make a mistake, and then correct it, and they go back to the task, and they don't repeat the mistake. So sometimes what we do in machine learning, so if the data miner makes a mistake, we feed more data, assuming that it will learn better and it will not overfit. So it doesn't work like that. So maybe we should understand what's going on in the field, where that problem comes from, and then rebuild the model. So I just would like to give you a couple of examples from our own experience and research, that in cases where we dealt with big data and didn't make sense, and we had to go back and analyze a situation and repeated our model and experiments. And in most of the cases over these 13 years that we've been building these models, we either started with small data and understood the situation and applied it to bigger data sets, or vice versa. Whenever we handled a bigger data set, we always went back to the smaller one, understood the situation, and then rebuilt our models. So this example is about sampling. Many years ago, with a colleague, Tim Menzies and his team, and my students, we tackled the problem of having small data in organizations. Because when you start data analytics in software development organizations, the biggest problem, the biggest hurdle is, oh, we don't have enough data. And yeah, we can start collecting, but we don't have a tool. Yeah, we can build the tool, but it takes 3 years to collect the right amount of data and the right format of data. So we wanted to show empirically that how much data these guys would really need to have robust models, and is it really huge amount of data that they had to collect and build models. And our experiments show that, with different sampling techniques, as small as 50 data points in this particular, data sets were good enough to have robust models to make predictions. This was a defect prediction study. So it only, as I said in my earlier point, that it only needs for us to have meaningful data to learn and build theories from. And we need to connect the dots by understanding what's going on in the field. So that's why field studies and talking to people on the field and understanding their processes is really important in building these models and systems. And that's the only way we can cover some overlooked areas in the development life cycle. So there's another example that we were working with IBM in Toronto labs, and they wanted to predict defects in certain categories. And so we couldn't find any good category, standard categorization, defect categorization in the literature. And the data was not categorized as such either. So we used what we had available at the time, and the model we built out of that big data set was totally meaningless. And so we went back to the company, and we had meetings with the developers and managers, and we understood, what those categories and the defects meant, and so we defined certain categories and rebuilt our model, and then we had much more meaningful results. By doing that, not only talking to people, we looked at all kinds of statistical analysis, correlations between different defect categories and attributes in order to better understand their defects. So our lessons learned was it was really important for us to meet and understand different stakeholders' point of view in the organization. And also we learned that one piece of information we gathered from one side of the organization may not be transferable to the other one. So we can have a generic model, but we need to understand the context to make sense out of that model. And another recent problem we had was, again, when we wanted to measure the confirmation bias of software engineers. So our goal was how biases did affect people's quality of work, and what kind of factors were effective in defining confirmation bias. So we wanted to come up with a quantification methodology of confirmation bias, and that was our challenge. So we defined a methodology, and we came up with a metric suite to measure confirmation bias. And we come up with a formula to drive one single metric. And we did some statistical analysis. And again, our results didn't turn out to be meaningful. And so it was all over the place. So for example, people who had very low confirmation bias levels and their team were producing lots of defects, or vice versa, people who had high confirmation bias, people who had high biases, they didn't show any defects or something like that. So we went back to each one of these settings and companies, and so we talked to the managers and people, and we have seen that there were certain outliers in each team. And we looked at their workloads, and we have seen that although people were experienced and they touched majority of the code, etc., since they were so exhausted and their load was so high, their scores were very low. And so we shouldn't have done the test at a different time, or we should have excluded these people in the analysis because it didn't make sense. So we removed these outliers and repeated our results again, and then it was much more meaningful. And our lessons learned in this case was, again, we had to understand the people on the field. So it wasn't about, number crunching, getting some numbers, data, and using certain algorithms and statistical methods and produce results. So we really needed to understand what was going on in the field before we do anything. And also, in this type of defining a metric set or a single metric, etc., another lessons learned was we had to go to different domains, different organizations, just to make sure that we covered all aspects or different things that we didn't think during the model construction. So in conclusion, this is a typical process in dealing with data, whether it's big or small. So we collect raw data from some source or certain sources. Then we process that data, clean it, and we do some exploratory analysis of how the data looks like, the distributions, means, medians, and all that stuff. And then we employ certain techniques to make predictions and decisions. So after we apply these techniques, we take the results and give it to management, and they make certain decisions. And if we are a sales organization, for example, maybe with these results, we may be coming up with new products, data products. So in between data cleanup and exploration, I think we need to do these case studies and understanding the field before we construct these models. And this would give us much more insights and enable us to uncover certain hidden patterns in the data. And so I would say that all you need is meaningful data, whether it's small or big, and we can build theories from the data that would be available to us. And we need to understand the underlying concepts in anything we do. And going forward, we should combine big data techniques with local models to make most effective use of these models. So, thank you.